Okay, so in this video, we're going to look at the factor theorem. This is the next sort of tool in our polynomial factoring toolkit. We've already seen how to divide polynomials. We would divide like a cubic by some linear term, and either it had a remainder or it was a factor, right? It had a non-zero remainder or it was a factor. But is there a way to tell which linear terms we could divide a polynomial by, a higher degree polynomial, and it will be a factor, right? If we're trying to factor the thing completely so that we can graph it, find the roots, etc., how could we tell which linear factors, which linear terms we should try dividing it by? And this is where the factor theorem comes in. It tells us that for any polynomial p of x, x minus a is a factor of p of x if and only if p of a is equal to 0. So if p of a is equal to 0, x minus a is a factor. That's the really sort of significant direction of this biconditional, as we say. The other one is pretty straightforward, right? If it has a factor of x minus a, you plug in a, and the whole thing is equal to 0, so p of a will be 0. But the sort of meat of this one is that if p of a is equal to 0, then x minus a will be a factor of p of x. We proved this in another video. In this one, we're just going to kind of give you an idea of why it's true. If we do our polynomial division, using what we know about polynomial division, we've seen that if we have a polynomial p of x, and of course the degree of p is going to be bigger than or equal to 2, so p of x is equal to x minus a, we do our division, and we're making the degree bigger than or equal to 2, so that we can divide it by x minus a, which is a linear term. We've seen with polynomial division that we can write this as x minus a times some quotient polynomial, q of x, and then plus a remainder. And the remainder is going to be a real number, right? Because its degree has to be less than the degree, strictly less than the degree of x minus a. This is the degree 1. This is degree 1, so this will be degree 0, or a constant. The degree of q will be 1 less than the degree of p, whatever that is, and we get this division statement. And what does this tell us? This tells us that p of a is equal to, well, a minus a, right, when we plug in a for x, and then times q of a, and then plus r. And what's this equal to? Well, a minus a is equal to 0, right? So this thing is equal to 0. And then it doesn't matter what q of a is, right? Anything times 0 is equal to 0. So this whole thing is just equal to r, right? P of a is equal to r. And this actually is something called the remainder theorem, which is closely related, right? The remainder theorem, which we do have a separate video on, but it's the same exact thing. The remainder theorem says that p of a is going to be equal to r, right? Because of this. And then what does the factor theorem say? Well, it says if r is equal to 0, then of course p of x is equal to x minus a times q of x. So it's a factor, right? X minus a this is what it means for x minus a to be a factor of p, right? P is equal to x minus a times some other polynomial q of x. So if r is equal to 0, then p of x is equal to x minus a times q of x. X minus a is a factor, right? The other direction is that if, and this is sort of the trivial one, but if p of x is equal to x minus a times q of x, then of course p of a is equal to a minus a times q of a, which is 0, times q of a, which is 0. So this is the other direction. This is an if and only if. The really useful part of it, though, of course, is that you can check whether x minus a is a factor of p just by plugging in a to the polynomial p and seeing if you get 0. And then, of course, if you do get p of a is equal to 0 and you're trying to factor the thing, then you can divide it by x minus a. We can use polynomial division to divide it by x minus a, and, which is what we're going to do right now, we're going to check some, and if they're divisible, we will divide them. And then you can repeat this process. How you find the a's is a different matter. This is what we talk about in the rational roots theorem video. This is the third and sort of final piece in our polynomial factoring toolkit. How do we figure out what the a's are? But suppose we think that 2 is a factor of the polynomial. So this is 1. We have p of x. We have p of x is x cubed minus 3x squared minus 4x plus 12. If we think that x minus 2 is a factor of this, and we want to check it, well, we're going to compute p of 2, right? P of, it's x minus a, we plug in the a. It's the value of x that makes the factor 0. We plug in p of 2, and we get, well, this is going to be 2 cubed minus 3 times 2 squared minus 4 times 2 plus 12. That is p of 2. And 2 cubed, of course, is 8. 3 times 2 squared is 12, so we're subtracting 12. And then we're subtracting 4 times 2, which is 8. And then adding 12, and so this is equal to 0, right? X minus 2 is going to be a factor of this thing. We have 8s canceling and 12s canceling. This is equal to 0. And this means that x minus 2 is a factor of p, which is x cubed minus 3x squared minus 4x plus 12. So the next step is let's divide it. Let's do the division. Let's divide x cubed minus 3x squared minus 4x plus 12 by x minus 2 with quotient and remainder. So same process we've always done. We set up the division statement. This is the divisor, x minus 2. This is the quotient, and here would be the remainder, but we know the remainder is going to be 0. We are guaranteed that if we don't make a mistake here, the remainder will be 0. So we don't actually, I'm not going to put the r in here. We're just going to be figuring out what the quotient is. And we do the same thing we do every time with this. We put x squared here to multiply in by the x and get the x cubed that we're trying to match there. So this is going to be x cubed when we multiply these together. And that's what we're trying to get here, x cubed and x cubed. And then, of course, the x squared multiplies by the negative 2 and gives us negative 2x squareds. We're trying to get negative 3x squareds. So the next term that we get out of this process has to be negative x squared. We need a negative x squared here. What do we multiply x by to get negative x squared? Well, it's going to be negative x. So that's the next thing that goes in the bracket. It multiplies through by the x, gives us the negative x squared. So we have the right number of x squareds, but then it also multiplies by the negative 2, and it gives us plus 2x. So we get plus 2x. We're trying to make negative 4x, so we need negative 6x. So the next thing that we put inside the bracket, I should have put this in yellow there. The next thing we put inside the bracket to make that negative 6x has to be a negative 6, right? I need a negative 6 to multiply by that x to get negative 6x. That, of course, works, right? We now have the right number of x4s. And then the negative 6 multiplies by the negative 2 and gives us positive 12. So the constant is positive 12, and that is the correct constant, right? This one works. This one works because we knew that x minus 2 was a factor, right? Because p of 2 was equal to 0, we were guaranteed to have this happen. So our final division statement for this is going to be, and now we factored this cubic down to a linear term and a quadratic, and we can continue to factor the quadratic. What's that going to be equal to? Well, if you haven't seen the videos on factoring quadratics, do take a look at those, but we can see that this thing is actually going to be equal to, and I should say we can see this if we've done a ton of practice, you start to see them. That's why doing it the long way is such a good idea. Doing it the way that you understand what you're doing, you start to see this kind of numbers in the matrix like this. But if you can't see it, if you haven't done a gigantic amount of practice yet, of course, and then we can use decomposition, and we have videos on that, of course. We can use decomposition to show that this, or to figure out that this is equal to x minus 3 times x plus 2. And now we can do whatever we want with it. We can graph it. We can find, if this is the derivative of a function, we're trying to find the intervals of increase and decrease. We can do that. But we are through the full process of factoring this cubic polynomial. Of course, we haven't seen where we would have guessed, why we would have guessed 2, right? Where did 2 come from? That's the rational roots theorem video, so please do check that out. And then we'll be back in the next one to do, we have a couple more problems here, including a K question, so getting a little bit creative with this one.